IEC 62443 is a family of standards focused on cybersecurity for industrial automation and control systems. These systems monitor or control physical processes in manufacturing, energy, water, transportation, buildings, and other operational environments. Their security must account for safety, availability, reliability, process integrity, and long equipment life cycles. The standards provide a structured way to discuss industrial cyber risk across organizations and technical disciplines. They address security programs, system design, risk assessment, product development, technical capabilities, integration, and service delivery. IEC 62443 is therefore broader than a list of firewall settings or product features. Asset owners use the concepts to establish governance and determine what protection their operations require. Integrators translate those requirements into an architecture and commission system. Product suppliers build security capabilities into components and maintain secure development practices. Service providers support systems without weakening the controls around them. This division of responsibility matters because no single product can secure an industrial operation. A capable component can be configured poorly. A well-segmented system can be exposed through unmanaged remote access. Strong policy can fail if teams cannot produce evidence that controls are implemented and maintained. IEC 62443 should be treated as a risk-based, lifecycle-oriented framework for disciplined engineering. It does not eliminate uncertainty or replace knowledge of the process. Its practical value comes from connecting organizational responsibility, architecture, technical requirements, verification, and ongoing operation using a common industrial cybersecurity language. Industrial cyber risk does not fit neatly into traditional information security assumptions. A loss of confidentiality may expose engineering information, but a loss of system integrity or availability can also affect machinery, product quality, safety, environmental conditions, and essential services. Security decisions must be evaluated against physical operations. OT environments combine specialized control devices, conventional computers, industrial networks, safety functions, cloud services, remote vendors, and human operators. Equipment may remain in service for decades. Patching and architecture changes may require vendor support, testing, maintenance windows, and carefully planned recovery. Without a common framework, each organization or supplier may define security differently. An asset owner may request a secure system without describing risk or acceptance criteria. A supplier may describe a component as secure without explaining its capabilities or assumptions. An integrator may deliver a working process while leaving remote access and account ownership unresolved. IEC 62443 creates a common language for these conversations. It connects business and operational risk to system requirements, supplier capabilities, service responsibilities, and lifecycle practices. It encourages teams to define boundaries, identify required communication, select protection based on context, and preserve evidence that decisions were implemented. The standards also reinforce that cybersecurity is continuous. Operations change, software ages, vendors release updates, and threat conditions evolve. Security must be considered during design, procurement, integration, commissioning, operation, maintenance, and retirement. IEC 62443 exists to make that shared work more consistent, accountable, and suited to industrial reality. IEC 62443 is a standards family rather than one checklist. Its parts address different subjects and audiences while using related concepts. Understanding that structure helps teams select the material relevant to their role instead of treating one document as the entire industrial cybersecurity program. The general category establishes shared concepts, terminology, models, and measures. These foundations help asset owners, engineers, suppliers, and assessors use terms consistently. Policies and procedures focus on organizational and operational practices, including security programs and service provider responsibilities. System-focused material addresses risk assessment, secure system design, security levels, and technical requirements for industrial automation and control systems. This is where concepts such as zones, conduits, and system security requirements become central. Component-focused material addresses secure product development and technical capabilities for software applications, embedded devices, host devices, and network devices. The categories are connected. An asset owner's risk assessment creates system requirements. An integrator designs and verifies an architecture that addresses those requirements. Product suppliers provide components with appropriate security capabilities and development evidence. Service providers maintain the system within defined controls. A practical implementation starts by identifying applicable roles, lifecycle stages, and system boundaries. Teams should use the applicable current standards and organizational requirements for detailed work. This introductory course explains the framework, but it does not substitute for the official documents, project-specific engineering, or formal assessment criteria. IEC 62443 distributes cybersecurity responsibility across the industrial lifecycle. The asset owner owns or operates the industrial environment and remains accountable for understanding operational risk, defining security requirements, approving residual risk, and sustaining the security program. System integrators and automation solution providers turn requirements into a working architecture. They select and configure components, define zones and conduits, establish accounts and communication paths, test controls, and deliver documentation. Their work must satisfy both cybersecurity objectives and process requirements. Product suppliers develop hardware and software used in industrial systems. They are responsible for secure development practices, documented capabilities, vulnerability handling, update information, and clear assumptions about how a product should be deployed. A product's capability is useful only when the system design uses it correctly. Service and maintenance providers preserve or modify the system after commissioning. Their remote access, tools, credentials, change practices, and incident communication become part of the security architecture. Contracts and operating procedures should define what access is permitted, how it is approved, and what evidence must be retained. Shared responsibility does not mean vague responsibility. Projects should assign ownership for risk decisions, configuration, accounts, patching, backups, monitoring, incident response, documentation, and end-of-life planning. Handoffs between suppliers, integrators, and operators are common failure points. Acceptance criteria should verify that required controls work and that the asset owner receives the information needed to operate them. Security is strongest when every role understands both its obligations and its dependencies. No participant can transfer all risk to another party, and no single participant can manage the entire lifecycle alone. Zones and conduits turn risk analysis into architectural boundaries. A zone groups logical or physical assets that share security requirements based on factors such as function, criticality, consequence, ownership, and exposure. A zone should represent a meaningful trust decision, not merely an existing subnet or room. A conduit is a controlled communication path between zones. It carries the data and services that the operation requires while enforcing the boundary's security expectations. Teams should document approved sources, destinations, protocols, direction, purpose, users, and administrative ownership. For example, an enterprise reporting system may need production data from a site historian. That requirement does not justify direct enterprise access to controllers. An intermediary service in an industrial DMZ can replicate required data while reducing reachability toward lower-level control functions. Zone design should distinguish systems with different risk and capability. Safety functions, control areas, engineering services, remote access, wireless devices, and legacy equipment may warrant separate treatment. Conduits should also account for administration, updates, backups, authentication, and vendor support, not only routine production traffic. Segmentation technology implements part of the design, but a firewall alone does not create a defensible zone. The boundary needs current inventory, documented flows, secure configuration, monitoring, ownership, and change control. Teams must also test that restrictions preserve timing, redundancy, failover, and recovery. Review zones and conduits when architecture or risk changes. Cloud analytics, new vendors, temporary maintenance links, and production expansions can introduce paths that bypass the intended model. The objective is necessary, limited, observable communication between assets with clearly understood trust relationships. Security levels express increasing degrees of protection for industrial automation and control functions. They provide a structured way to translate risk into security expectations. A higher level represents resistance to a more capable, motivated, and well-resourced threat, but it also requires stronger capabilities, implementation, and evidence. The target security level describes the protection required for a zone or conduit based on risk. It should result from analysis of threats, consequences, exposure, existing safeguards, and risk tolerance. It is not selected simply because a system is important or because a supplier markets a high level. A component's capability security level describes the security capability it can support when correctly configured and used. The achieved security level describes what the integrated and operated system actually provides. These concepts are related but not interchangeable. A capable device can be undermined by poor architecture, shared credentials, weak remote access, or disabled features. Security level selection should be specific to the foundational requirements and the system context. A zone may need particularly strong integrity and restricted data flow while having different confidentiality needs. Independent safety functions, physical controls, and operational procedures also influence risk, but they should be documented rather than assumed. Verification matters. Teams should be able to trace a target level to risk decisions, requirements, design controls, component capabilities, configuration, test results, and operational procedures. Changes to connectivity, process consequence, threat conditions, or components may require reassessment. Security levels are therefore decision and engineering tools. They do not certify an entire facility with one number, and they do not guarantee that a system remains secure throughout its life. IEC 62443 organizes technical security objectives into 7 foundational requirements. Together they provide a balanced view of identity, authorization, integrity, confidentiality, communication, detection, response, and availability. The required strength of each objective depends on the zone, conduit, risk, and selected security level. Identification and authentication control establishes who or what is requesting access and verifies that identity. Use control determines what an authenticated user, device, or process is allowed to do. Industrial systems may have technical limitations, so architecture and managed gateways may need to enforce controls that individual devices cannot. System integrity protects systems, software, configurations, and communications from unauthorized or accidental change. Data confidentiality protects information from unauthorized disclosure where that disclosure creates risk. Confidentiality matters in OT, but it must be implemented without undermining required visibility, timing, or recovery. Restricted data flow limits communication between zones and through conduits. It supports segmentation and containment by allowing necessary flows while denying unnecessary paths. Timely response to events addresses the ability to detect, record, communicate, and respond to security-relevant activity. Useful monitoring requires ownership, context, and practiced procedures. Resource availability protects the capacity and functions needed for safe, reliable operation. This includes resilience against resource exhaustion, component failure, and disruptive security controls. Redundancy, backup, recovery, and graceful degradation may all contribute. The foundational requirements should be engineered as a system. Strong authentication without availability planning can lock operators out during an emergency. Excellent logging without response ownership produces little value. The objective is a set of mutually supporting controls aligned with the industrial process. Practical IEC 65443 adoption begins with scope and ownership. Define the system under consideration, the physical process it supports, responsible organizations, lifecycle stage, and risk decision makers. Build an asset inventory that includes devices, software, firmware, communication paths, remote connections, suppliers, and operational dependencies. Perform risk assessment with engineers and operators. Identify credible threats, vulnerabilities, existing safeguards, process consequences, and required recovery. Use the results to define zones, conduits, target security levels, and requirements. Avoid copying an architecture from another site without confirming that functions and consequences match. Review the architecture for unnecessary connectivity and uncontrolled trust. Design segmentation, secure remote access, administration, monitoring, backups, and update pathways together. Procurement and supplier requirements should state expected capabilities, evidence, vulnerability handling, support periods, and integration assumptions. During implementation, configure component security features, remove unused functions, manage identities and privileges, document exceptions, and test controls under realistic conditions. Acceptance testing should verify security behavior as well as process operation. The asset owner needs accurate diagrams, account ownership, configuration records, backup procedures, and recovery information. Operation requires change control, vulnerability management, monitoring, incident response, periodic access review, backup testing, and lifecycle planning. Evidence should show what was implemented, who approved it, how it was tested, and how deviations are managed. Metrics should support decisions rather than exist only for reporting. Organizations do not need to solve every issue at once. Start with high-consequence systems and pathways, create achievable improvement plans, and integrate cybersecurity with existing engineering, safety, reliability, and maintenance processes. IEC 64543 works best as an operating discipline, not a one-time documentation project. IEC 62443 is a family of standards for industrial automation and control system cybersecurity. It connects organizational programs, risk assessment, system architecture, product capabilities, service responsibilities, and lifecycle operation. It is not a single checklist or product. Responsibilities are shared but must remain explicit. Asset owners define risk and sustain the program. Integrators implement and verify secure systems. Product suppliers provide secure development practices and component capabilities. Service providers maintain access and changes within approved controls. Zones group assets with related security requirements. Conduits control communication between those zones. Security levels translate risk into protection expectations, while the foundational requirements organize identity, use, integrity, confidentiality, restricted flow, event response, and availability objectives. Successful implementation depends on evidence and engineering. Inventory assets, understand the process, assess risk, configure capabilities, test controls, govern remote access, monitor meaningful activity, maintain backups, control changes, and plan for incident recovery and technology retirement. The central lesson is collaboration across the lifecycle. IEC 62443 gives engineering, operations, cybersecurity, suppliers, and management a common structure for making defensible decisions. The official standards and environment-specific analysis provide the detail. Disciplined ownership turns that detail into resilient industrial operations.